Recording now. So as I was saying, can be super complex or super simple. And a single point does actually constitute a graph. So what you're looking at on the screen then is just a 3-vertex, 2-edge graph. And our initial language goes around such things as our vertices will, like they are in geometry, we give them capital letters to be able to refer to, and adjacent vertices are joined by an edge, are connected by an edge. So, for instance, these vertices here, we wouldn't call them adjacent because they're not connected. As soon as they're connected, then we can call them adjacent vertices. And adjacent edges will share a vertex. In this case, those two being adjacent will share this vertex here. That's all we can really extract from diagram 1. First thing we look at is simple graphs and what defines a simple graph. So a simple graph has to satisfy these two conditions. So no vertex joined to itself and no multiple edges. Multiple edge graphs are called multigraphs. Now at the moment, I've just got three points down here. So not much is happening with this graph at the moment. It is a graph. It's a 3-point graph, no edges. 3-point, I should say vertex, sorry. 3-vertex graph, no edges. To make it a simple graph, I mean, that is a simple graph already because there's no loops and there's no multiple edges. So that is a simple graph. This is a simple graph. This is still a simple graph. Still a simple graph. Now, I'll make it not simple by putting a loop on one of my vertices. Now it's not simple anymore because a vertex leads to itself, is joined to itself. So that would take it out of the simple category, and so would this. So if I've got more than one way of getting from vertex A to C in this case, I've got 2 paths between A and C, so it's not simple. So what, if you want to have a look at, this is a counterexample or a non-example of a simple graph. So it's a not simple. And if we have a look at another, I just take a graph that does something like this and then has a loop to itself, would also make it not simple because of that. So they're the two. If we're looking for simple graphs, that's all we're looking for. Just no loops and no double edges, no multiple edges, sorry. Okay, moving on, adjacency tables. Adjacency tables are a way of representing, so this is the table here on the right. So graphs to tables, tables to graphs. We do need to be able to work both ways. Okay, so I've drawn a graph here, A, B, C, D. Is it simple? Turn your mics on, folks. Yes or no? Simple? Turn your mics on, please.
No.
All of you turn your mics on.
No.
Winnie, leave your mic on, please. Raylene's gone. Okay, so I'll ask again, simple or not?
No.
Why not? Roger? Roger, why not?
Because a simple graph has to have, what's it called?
Yeah, so what makes this not simple? There were 2 things. We can't have a vertex joined to itself, and we can't have multiple edges between two vertices. So what makes this not simple? Where do you see it not breaking the rules?
It has lone points, like if you could see B and then AD, there's two lines joined together.
AD, there's no problem with B at all, but AD having two paths between them, that makes it not non-simple. That's right. Is there another one, Winnie? Is there another something going on here that makes it non-simple?
Yes, C.
That was for Winnie. But at what's happening at C?
There's like a point joined to itself.
All right, it's looped to itself. Okay. So that's transfer. So what an adjacency table does is it, okay, so we've got in the table all the vertices. And what it's a grid system. So we're labeling with numbers the number of ways of getting from one point to another. So in this first cell here, this first space A to A, what we're writing down there is how many ways are they getting from A to A. So are there any loops on A? So there are no loops on A, so that's where the 0 comes from there. From A to B, I've got A to B here, I've got one path. So that's why I've got one here. So if we just follow it around, it's all going to be, if it's a simple graph, oops. If it's a simple graph, there are not going to be any down the diagonal here, they're all going to read 0, because if there's a 1 there, that means it's looping to itself. So in a simple graph, and you see I've made that note there, these will all be 0s. The other thing is that there will only be 0s and 1s in other positions. Because if there's a 2, such as A to D here, that means that I've got two paths between A and D, 1, 2. So it's symmetrical. This graph, the table is symmetrical. So it's a simple idea, but all it does is it tells us how many paths there are, how many ways there are from one point to another, how many edges take me from one point to another. Oh, the other thing I've noticed in here, I've noted, is the degree of each of my vertices. Now, the degree of a vertex is the number of edges that come out of a vertex. The number of edges that come out of a vertex. So if you're looking at A, let's have a look at A. We are looking at 1, 2, 3, 4. Do you see there's 4 edges coming out of it? So the degree of A is 4. The degree of D, we just look at D and just see how many edges are popping out. So we've got 3. And so what we say is the degree of D, or deg D, is equal to 3. This is represented in our table. Have a look at our table. If we sum our column, like look at the column of A, 0, 1, 1, 2. I've written the sum in here. That gives me the degree of the vertex A. The only difference, anytime this doesn't work as a sum, have a look at C. 1, 2, 3, yet my degree of C is 4. Now the reason for that is I have to count this loop twice, because as I look at C, I've got 1, 2, 3, 4. So if you've got a loop, that's in terms of the degree of that node or vertex, that counts twice. So this number here is 1, we have to count twice. 1, 2, 3, 4. Is that all okay? Good so far?
Yeah.
All right. The number of edges coming out of a vertex is the degree of that vertex. Right now, the degree sequence is the list of degrees for each vertex in a graph. So the degree sequence, usually written in descending order, is for my 4 vertices. I'm just writing them. I've got 4, 4, 3, 1. That's called the degree sequence. Really, this is we'll keep referring back to these terms as we go through the course. But and so you in terms of trying to, you wouldn't beat yourself up trying to memorize these terms at this stage. But it's like an introductory lesson to graph theory. This one. We will get to practice this as we go through, and they'll become fairly familiar pretty quickly. Now we get to do a proof here. There are some proofs in graph theory that we need to rehearse, a little bit like, where was it? We had to do some, didn't we, back in number theory? So in graph theory, there are some proofs, and we are going to use some of our proof methods. And actually in this lesson today, the pigeonhole principle and induction pop up, although we can use normal induction, I think, for the one we're going to use. So in a simple graph, there will always be two vertices with the same degree. That's the theorem. Now the proof of that theorem, so what that means is if we look at our degree sequence, we're always going to have two that are equal in a simple graph. Simple graph. Okay, so do you want to, let's go through the proof of that. Two vertices with the same degree. So if you think about a simple graph, you got n vertices, whatever that may be. 1, 2, 3, 4, 5. Now what is a simple graph? Is that a simple graph? Yes, no, don't know. Does it break any of either of the two rules?
No.
What are the two rules? Loops and multiple edges. Does it break any of those?
No. So
No. So you come from a position of, does it break those rules? So it doesn't. So that is a simple graph. What are the degrees of each of those nodes, those vertices? What's the degree of our vertices?
0.
Sorry? What's the degree of A?
0.
0. Degree of B? Degree of B?
You keep cutting out, Mr. Sherwin. It's really hard to.
Yeah.
I'm cutting out, am I?
Yeah.
I'll have a look at I'll change my Wi-Fi setting. A sec, I'll just change over. Okay, that might be a stronger connection. Is that okay?
Yeah.
So I was asking about the degrees of our vertices A, B, C, D, E. So the degree of vertex B.
Wouldn't they all be 0? Because they're not.
Yep. Okay. Now what have I got for B? What's the degree of B?
1.
Let's try it 1. All right. And okay, let's see what we've got here. Let's try and keep it simple. Still simple?
Yeah.
Is it possible then, what we're trying to do is, the theorem is that there's always going to be two vertices with the same degree? At the moment, we've got what? E, B, C are all degree 2, D and A are degree 1. How many? So now we're going to start thinking. As soon as you're asked to prove something where you have to prove that you have to show that there are at least two with the same number, that screams pigeonhole, doesn't it? Because that now we're trying to load up more pigeons and pigeonholes, and we have to have some doubling up. So is this one of those situations? So if in this case we've got 5 vertices, so they're our pigeonholes. What are the possibilities for the degree of my vertices? So what's the lowest we can have for our, go to this 5 example for A, B, C, D, E. So we can have a 0 degree. Is that right? Is that right? Can I have a 0 degree vertex?
Yeah.
It's possible. Okay, let's make one then. There's a 0 degree. If I've got a 0 degree vertex, what's my maximum? What's my maximum going to be?
3.
3? So I've got to leave, say, D out. So if I just join, so that means that, say, the point C, I could join him up to A, like this. Are we still okay? Are we still simple? What do you think? Are we still simple? I've broken either of the rules yet? No, we're okay, aren't we? What's the degree of C? Can I make C any higher? Can I join him up to anything else while keeping it simple?
No.
No, so the highest degree of C would be 3. Is that right? So our minimum, if 0, would be, our maximum if 0 would be 3. So how many are there? 0, 1, 2, how many pigeons do we have? 0, 1, 2, 3, so I've got 4 pigeons.
Hi, Mr. Sherwin.
Who's that?
I'm back.
Oh, that's right. Hi. Welcome back. So there's 4. Okay, so it could be 0, 1, 2, or 3. So there's 4 pigeons, and I've got -1. Maximum degree of 3. Does that sound 1, 2, 3, 4, 5? Okay, sorry. So we've got that's not making sense. Sorry. There's 5 pigeonholes at the moment and 4 pigeons. No, it's the other way around, isn't it?
Yeah.
It's the other way around. The vertices are the pigeons. Vertices are the pigeons. So we're fitting into our 5 vertices. Sorry, into our 4 degrees, we're fitting 5 vertices. So our 5 vertices have only got 4 choices of degrees. So one of them, at least 2, have to have the same. Sorry, is that all right or not? I mixed up my pigeons and pigeonholes here. I'm always doing that. All right, so I've got A, B, C, D, and E. I've got 5, and they need to the choices for the options for degrees are 0, 1, 2, or 3. So they have to, at least 2 have to share the same number of degrees. So if we look at it, that's if one of them is left alone. If we join all of them up, so they've all got, so the minimum is 1. Then now I can join C's got a maximum. So now my maximum is 4. My eraser's not working. So if I've got a 0, if I've got a vertex on its own, then my maximum in this example would be 3. If I've got a vertex, if I don't have any vertices on their own, then my minimum degree is 1 and my maximum is 4. Either way, I've got 4 options, 4 numbers of degrees. So I've got either 1, 2, 3, or 4, and I've got 5. I've got A, B, C, D, and E are my points. So these have all got to go somewhere. So there's going to be at least 2 that have got the same number of degrees. So pigeonhole principle works for that proof. And it's in blue is what it is. In blue, I've written out what it is in terms of n vertices. So if I've got, if my minimum degree is 0, then my maximum degree will be n minus 2. So I've got n minus 1 pigeonholes, and n vertices, and n minus 1 pigeonholes being the number of degrees, the number of choices of degree.
Is this just the proof of that theorem, like, or is
The
this
proof of this theorem? Yeah.
Are we likely to get questions?
Yep.
Like proving.
You're likely to get a pigeonhole principle proof. Yes.
Okay.
In graph theory, that's pretty commonplace.
Like the exact same proof, or like would they?
No, no, maybe not exactly the same, but one that would be similar.
Okay.
Because we're often in graph theory, we're looking at situations where we've got edges and vertices, and so quite often we're met by some kind of theorem that needs a pigeonhole principle application. So this is a good example of such a thing.
Mm-hmm.
So in essence, we're just going to have more options for less options for degrees than we have vertices. So we have to overload one of those at least by 1. Okay, so that's a proof just worth being familiar with, and certainly the pigeonhole principle being reacquainted with that. All right, connected graphs. So connected graphs, you've got a path from every pair of vertices. So you can get from one vertex to another in a connected graph. Now the example here is not connected. This is a counterexample because I can't get from A to A, B, C, D. I can't get from A to D, or I can't get from A to E. I can't get from B to D. So this is a disconnected graph. So right here, not connected. As can't get from A to E, or in fact E or D to any of A, B, or C. So that's not connected. An example of a connected is just, we can just join up. As long as we can get from, that'll be connected. We just can't have any vertices that are left floating. Okay, connected. Complete graph. So a complete graph is where every pair of vertices are joined by an edge. So you can get from any vertex directly to any other vertex. So KN, that's just our notation. So if I've got 3 vertices, I need to, for a complete graph, I just need a path between each pair. So that's complete. So this is a K3. An example of a K4. Okay, I've got 2 more pairs to connect, haven't I? So I can go here, and I can either go right across the middle, or I can go around. This is okay as well. So there's a K4. Okay, so the number of edges in a complete graph, there's a nice way of calculating. I've got 3 vertices here, and I've got 2 edges. So I've got 3 vertices and 2 edges. Over here I've got 4 vertices. How many edges do we have? 1, 2, 3, 4, 5, 6. So that's the way to calculate this number of edges, this value here from the number of vertices is to take its NC2. So this 4 vertices, 4C2 is equal to 6. What do we got here? 3C2 is equal to 3.
Should be 3 edges, right?
Number of edges, yeah, that's right. Number of edges from n vertices in a complete graph will give us, will be NC2. Let's think about why that is. If we're joining each, if we've got 4 vertices and we're joining each pair of those vertices, we're finding out how many pairs, are we not? How many 2s there are, how many combinations of 2 there are from 4. So there's 6 edges because there's 6. There are 6 ways of grouping those 4 vertices into 2. Does that make sense? So if we call them sort of, if these are A, B, C, D, then really it's another way of saying how many ways are there of grouping them? How many combinations of A, B, C, D are there? That's A, B, A, C, A, D, B, C, B, D. What have I left off? C, D. There it is. So there are 6 combinations. We need to, and there are 6 edges because each of those pairs need to be joined. So that's why it is 4C2 or 3C2 or NC2, because it's exactly the same as calculating the number of combinations of 2 from n vertices.
But why 2? Sorry.
Because we're pairing them up. We're considering the vertices as pairs because they all have to be joined. So each pair has to have an edge. So if we know how many pairs there are, we'll know how many edges there are.
Okay.
Wait, how many edges for 3 vertices?
3C2, 3.
But you.
Oh, sorry, I've written 2 edges there, sorry. 3 vertices is 3 edges, wasn't it? 3C2, 3 over 2, which is 3. Sorry about that. So 3 edges for 3 vertices. Okay, that one will come back up later, and in fact, yeah, we use that a fair bit. So that's in a complete graph, the number of edges. All right, a bipartite graph. So bipartite, as its name suggests, bi split into 2, a partition of 2. So a graph that's split into 2 groups, if you like, 2 groups of vertices. Now I've split mine into blue and pink vertices here just to demonstrate. Now the vertices in a bipartite graph are only joined to vertices from the other group. They don't join, so there are no edges joining vertices from the same group. So this is bipartite at the moment, but we can mess it up by doing, I'll go in red. And if I did this, then it's not bipartite anymore. Still a graph, still plenty we can do with it. It just is not classified as bipartite because it joins 2 vertices from the same team, from the same group.
Mr. Sherwin,
Yeah.
can the edge like cross over or something? Is that why the other ones are not connected.
The edges can cross over. I could have drawn that here.
You can draw it
But
like that.
I can, I can. But I didn't because I don't like them crossing over.
So the down one, the one which you didn't connect, can be connected.
Which one's that?
The bipartite.
Oh, yeah. That's bipartite, but I could do more. We could put more edges in. Right, so I can, this is okay. This is okay. This is okay.
Right.
Now, that's bipartite. That's cool. But we just can't do this. That's not bipartite anymore. Okay, if every vertex from one group is connected to every vertex in the other group, it's a complete bipartite. So this is not, but it's complete if every vertex in this group connects with every vertex in this group. So I would also need to add this and this and what else? This and this. That would be complete.
Don't you have to connect the one on the edge to the other one on the edge too?
Did I miss one?
Like from...
Oh, this one to this one?
Yeah. Like
Yep.
that.
Thank you. All right, so the number of edges that we'll have in a complete bipartite graph will be... All right, so if I've got, how many edges do I have here? I've got 4 in the pink and 3 in the blue. So all 4 in the pink. 3, 6, 9, 12. Oh, I've missed one there. He's not gone to him either, has he? So I can, it doesn't have to be across. Sometimes it gets so muddled up, you can just go around. That is now complete. So there's 12 edges here, 4 times 3. So a complete bipartite graph will have R times S edges. Now that's, so the notation for a complete bipartite is K. K's complete. And if it's bipartite, we've got R comma S being the number of vertices in each group. So for me here, this is a K, 4, 3. And there are 12 edges. And there's going to always be R times S number of edges in a complete bipartite.
So in those bipartite ones, the 2 groups are always like the top one and the bottom one?
Yeah, it doesn't have to always look that neat, actually, Harriet. So you're going to see some that aren't quite so obvious.
Right.
And it can be quite difficult to establish whether a graph is bipartite because they are not always color coordinated and that sort of thing. So, but you're looking to identify groups of points that don't connect with each other, but do connect with other groups. So you're looking to try and isolate two teams of points, if you like.
Okay.
Yeah. We'll get some practice of that as well. Okay, so how are we going so far? Just a little recap. Simple graph, right? No vertex joins to it, so no loops, no multiples. Adjacency table, fine. We'll get a bit of practice of that. That's not a big deal. The degree, we're going to talk about the degree a lot. That's the number of edges that are coming into a vertex or out, right? It's just just count the paths out of a vertex. That's the degree. We can use the pigeonhole principle to prove this, that there's always going to be 2 vertices in a simple graph that have got the same degree. A connected graph you can get from one point to another. Usually fairly obvious to see, right? There's a disconnect, right? If there's two separate, if you can't get from one point to any other point. A complete graph is where every pair of vertices are joined up, and a bipartite is in 2 groups and doesn't join vertices from the same group. Okay, just a couple more. Yeah, go on.
In the disconnected graph, why can't it be joined?
Why can't it be?
Yeah.
Yeah, we're not. It's just it's a category of graph, Raylene. So it can be. It's just if it's not connected. So so I'm not sure what your question mean. What do you mean by why can't it be?
Why can't you connect
I mean,
A
we
and
can put a path in there to make it connected, but that's not the point. I'm showing you what is and what isn't.
Oh, all right. Okay.
So there's an example of a not connected, and here's an example of a connected.
Okay.
Is that okay? Yep. All right. So we've only two more things to talk about. That's trees and planar graphs. Okay. So a tree is a bit like you've seen trees before. You've seen family trees and tree diagrams. Whenever we did our factor trees, when we took a number like 28 and did all this. So trees are they're connected graphs, but they don't have any cycles. You can't make a circuit. So there are no closed paths. So these are examples of trees. They're connected, but there are no circuits. So I could make this not a tree by, say, connecting those 2 points there, because those 2 vertices. Because then I could make a circuit. I could go from one vertex to another along distinct paths and arrive back at the same vertex. So
Why
yeah, go on.
that tree kind of looks like the bipartite graph from above. Is that not when it's got all the connections, but before that when it was just the not complete one? Is that?
Yeah, so this here, Harriet, is bipartite,
Right.
isn't it? It's a bipartite tree. It doesn't need. Could I make it? All right, so it's bipartite at the moment. If I join those two, it's not bipartite anymore, isn't it? It's also not a tree. Can I make it not bipartite and not a tree? Sorry, can I keep it as bipartite but make it not a tree? Is that your question? Or did I just make that up?
Like, can you keep it as a tree and not bipartite?
I think, well, it depends. Keep it as a tree and not bipartite. So, all right, what about this example here? Is that bipartite? It's not, is it? Are there 2 groups of points here that don't connect to each other? I don't think there is. So that's a tree that's not bipartite.
Yeah.
Okay, so we're looking for the absence of circuits. Connected, no paths. All right, that's a tree. And there's a nice little proof by induction. I don't think we'll do it just yet. We might come back to this. That's a tree with n vertices has to have n-1 edges. Now, if you think about it, 1, 2, I've got 5 vertices here. 1, 2, I've got 4. 1, 2, 3, I've got 5 there. I've got 4 paths, 4 edges. If I take an edge off either of those, so if I'm taking this edge off, it's not a tree anymore. It's not connected, so I can't do that. If I add an edge on, I'm going to make a closed path out of it. So I have to have exactly n-1 edges in a tree for n vertices. And that's quite a simple induction proof, but it's one that we'll learn because it does pop up in exams. I don't think we'll do it now, though, because I think you're probably on overload at the moment. And there's only one other graph to discuss, and that's a planar graph. And this is, Raylene, comes back to why I didn't draw that diagonal up there before, because that would have made it non-planar. So it's a graph drawn in plane such that none of its edges cross paths. So this is planar at the moment. This is still planar. If I want to join these 2 points here, this is not planar anymore. Right, so this is not planar. Whereas This is all good. It's planar. I can join this guy to this guy. I can join him to him. This is all good. So as long as we don't cross paths, then we've got we have a planar graph. So again, that's just another definition to keep in mind for later in the game. Not planar. Not planar because of this, they cross paths. All right, that's all I've got for you, and that's probably a good thing because it's now 2:40. Exercise 6B is some practice. I don't think we've got some adjacency tables in there. It's really just going to be practicing some of the things that we've just talked about. In question 1, it's just state the number of vertices and edges. There's some adjacency tables, which are pretty straightforward, I think. Then I think we're going to be looking at, you have to draw some planar graphs, have a look at some bipartite graphs. I reckon you're going to be okay. There's quite a few questions, and I see you first thing tomorrow. Now we're going to lose Friday's lesson this week.
Why? What's that for?
That's related to getting off campus.
Oh God.
Friday's a moving day.
Mr. Shaw, if we cannot get off, could we make a true session, perhaps?
If you can't watch something, mate?
If I need to stay on campus, could we make a true session, perhaps?
Can we just get to the session if class is not running?
Is this related to being off campus, or is this just, can we have a tube session anyway?
What? To have a true session anyway on Friday.
Yeah.
Oh, on Friday?
Yeah.
You're talking about on Friday, Samson and David?
Yeah.
Yeah.
You are? Yeah. Well, let's talk about that tomorrow. We've got an hour tomorrow, so I'm just projecting a little bit. After tomorrow, we don't have a designated class until Monday. But there's a small enough number of us that I'm sure we can get together pretty much any time and have extra classes. So I think we can certainly arrange something. We're not behind on the course. We're traveling pretty well. We're in front, about a week ahead actually. So we're okay. But I'm totally cool with if everyone can attend, making up an extra class somewhere along the line. But should we think about that and talk about it tomorrow?
Yeah.
Sure.
6B, I just think, all right, I'm going to give you, I don't want to give you the whole exercise to do, but do as much of it as you can. And I'll see you in the morning. Sorry for all the definitions today.
Should be able to put
cool.
it up right after this, the video.
What's that, Raylene?
This video, the screen record.
The screen record?
Mm-hmm.
Yeah, sure. I'll put it on our OneNote page.
Right, okay.
Okay, I'll let you guys go. Have a good afternoon.
Thank you.
Thank you.
Yeah.
This Sherwin.
Yeah, mate.
Is this where the tree-free number comes from?
The tree from what?
The tree-free number, like the enormous number.
Tree free?
Yeah.
I don't follow. What's a tree free number?
It's like I don't know. Is it the same thing? The first thing that comes up is the Kruskal tree theorem. Is it different?
Well, it comes up on what? What are you looking at?
I'm looking at do you want to search up tree free?
Why did you, I'll search up tree free. Why did you search up tree free?
Nah, just it's something in my mind that just reminds me of that.
Okay.
Because tree is not a common word you see in maths.
No. What got you thinking about tree? Have you been tree free?
Yeah. I'm just wondering if that's related to
Tree free global size toilet paper?
No, just tree free. Maybe type number.
Number.
Yeah.
Tree free number.
Yeah.
Something to do with my Google search doesn't do anything other than I can see some images.
Yeah.
Looks like there's some kind of I trick on graph theory. They're the trees. But this tree, I've got nothing for tree 3.
All right, that's fine.
What have you got? What have you got?
I just
I've
know
got-
it's like an enormous number.
An enormous
know.
number.
Yeah.
I've got no reference to that on my search at all.
Oh, really?
How are we getting different searches?
I don't know.
Free or no, that's not it. Can you send me what you've got? Send me a link.
Oh, yeah, sure. I don't
And
think
it's
you
on
can
another
copy
page.
in the
I
chat.
never go past page 1 of my Google search.
Oh, you can. Oh, it's I put it in the chat.
Put it in the chat.
Yeah.
Oh, because I put in tree. No, Samson, I put in tree 3 as in FREE.
Oh, no.
I thought you were
3.
saying tree 3, but you're saying tree 3.
Yeah.
Tree 3 number.
Yeah.
Oh, right. Tree
Have you
3
heard of
number.
it?
No, I haven't heard of it, no.
Oh.
When the input is 1 or 2, the length of the longest possible tree is possible. When it's 3, the length is very, very, very long. What on earth's going on here? Oh, when just reading about it.
Something interesting.
Here's a simple progression. To understand the tree function, you have to first understand some of the functions that create big numbers. Nuts up arrow notation, iterated exponentiation. Have you got nuts up arrow notation?
I have no idea what it is, but it's just a number I know.
3 arrows. Okay, so it's this looks pretty intense. So it's saying here that that some guys put together 20 videos, so about 10 hours worth of videos, and to explain what the tree function does.
Well, it probably is.
And then eventually he tackles tree 3. So that seems to be like the culmination of all that. Tree goes very,
Does it look like something in the graph theory though?
I don't know, I'd have to explore it. It's got, the gist is the function returns the largest sequence of trees that you can build given an input of the different type, of the number of different types of seeds you can use to build them. So tree 1 is equal to 1 and tree 2 is equal to 3. Tree 3 is enormous.
Yes.
So have you heard about this before?
Yeah, I just like heard of this enormous number or maybe function. I don't know.
Free function. Yeah.
Yeah, but it's just
So when
some idea.
when
that
I started
came up.
talking about trees, you thought, oh,
Oh yeah, is this related? Yeah,
yeah.
yeah.
No, that's the first I've heard of it.
Okay. I just thought that's pretty interesting. So like,
Yeah. I like really big numbers, and it looks like it's a fairly complex function.
yeah, it would be, I guess.
But see, I've looked at a lot of student work, in explorations and things, and no one's ever done this. Maybe it'd be interesting to see what is involved,
Yeah, all right.
wouldn't
Well,
it?
anyway, here's an idea for you, but
Thanks,
I gotta go
Sams.
to my next class.
Yeah, you probably should, mate. I've made you a bit late.
No, that's right. It's cool. All right.
See you tomorrow. Cheers,
Yeah.
Samson. Bye,
See
mate.
ya.